Section 3. Computer Architecture. Introduction. In the previous study section, we learned that software is any set of machine-readable instructions that direct a computer's processor to perform specific operations. In this study section, we will learn about computer architecture, which is a set of disciplines that describe the functionality, organization, and implementation of computer systems. Learning outcomes. When you have studied this section, you should be able to describe what a computer architecture means, outline the history of computer architecture and the subcategories of computer architecture, explain the instruction set architecture, describe how computer performance can be measured. Computer architecture. Computer architecture involves instructions set architecture design, microarchitecture design, logic design, and implementation as shown. History of computer architecture. The first documented computer architecture was in the correspondence between Charles Babbage and Ada Lovelace, describing the analytical engine. Two other early and important examples were 1. John von Neumann's 1945 paper, first draft of a report on the EDVAC, which described an organization of logical elements, and 2. Alan Turing's more detailed proposed electronic calculator for the automatic computing engine, also 1945, and which cited von Neumann's paper. The term architecture in computer literature can be traced to the work of Lyle R. Johnson, Muhammad Usman Khan, and Frederick P. Brooks, Jr., members in 1959 of the Machine Organization Department in IBM's main research center. Computer architecture, like other architecture, is the art of determining the needs of the user of a structure and then designing to meet those needs as effectively as possible within economic and technological constraints. The earliest computer architectures were designed on paper and then directly built into the final hardware form. Later, computer architecture prototypes were basically built in the form of a transistor logic TTL computer, such as the prototypes of the 6800 and the PARISC, tested and tweaked before committing to the final hardware form. As of the 1990s, new computer architectures are typically built, tested, and tweaked inside some other computer architecture in a computer architecture simulator or inside a FPGA as a soft microprocessor, or both before committing to the final hardware form. Subcategories of computer architecture. The discipline of computer architecture has three main subcategories. 1. Instruction set architecture, or ISA. The ISA defines the machine code that a processor reads and acts upon, as well as the word size, memory, address modes, processor registers, and data formats. 2. Microarchitecture or computer organization describes how a particular processor will implement the ISA. The size of a computer CPU cache, for instance, is an organizational issue that generally has nothing to do with the ISA. 3. System design includes all of the other hardware components within a computing system. These include A. Data processing other than the CPU, such as direct memory access (DMA). B. Other issues such as virtualization, multiprocessing, and software features. Some architects at companies such as Intel and AMD use finer distinctions. A. Microarchitecture. Architectural layers more abstract than microarchitecture. B. Instruction set architecture, ISA, as above, but without assembly ISA which is a smart assembler that converts an abstract assembly language common to a group of machines into slightly different machine language for different implementations. 3. Programmer visible microarchitecture. Higher level language tools such as compilers may define a consistent interface or contract to programmers, using them abstracting differences between underlying ISA, UISA, and microarchitectures, e.g., the C, the C++, or Java standards define different programmer visible microarchitecture. 4. UISA, microcode instruction set architecture, is a family of machines with different hardware level. Microarchitectures may share a common microcode architecture and hence a UISA. 5. Pin architecture. Pin architecture functions are more flexible than ISA functions because external hardware can adapt to new encodings or change from a pin to a message. The term architecture fits because the functions must be provided for compatible systems even if the detailed method changes. Instruction set architecture. An instruction set architecture, ISA, is the interface between the computer software and hardware and also can be viewed as a programmer's view of the machine. Computers do not understand high-level languages which have few, if any, language elements that translate directly into a machine's native opcode. A processor only understands instructions encoded in some numerical fashion, usually as binary numbers. Software tools such as compilers translate high-level languages such as C into instructions. Besides instructions, the ISA defines items in the computer that are available to a program, e.g., data types, registers, addressing modes, and memory. Instructions locate operands with register indexes or names and memory addressing modes. The ISA of a computer is usually described in a small book or pamphlet which describes how the instructions are encoded. Also, it may define short, vaguely mnemonic names for the instructions. The names can be recognized by a software development tool called an assembler. An assembler is a computer program that translates a human-readable form of the ISA into a computer-readable form. Disassemblers are also widely available, usually in debuggers, software programs to isolate and correct malfunctions in binary computer programs. ISAs vary in quality and completeness. A good ISA compromises between programmer convenience, more operations can be better, cost of the computer to interpret the instructions cheaper is better, speed of the computer faster is better, and size of the code smaller is better. For example, a single instruction ISA is possible, inexpensive and fast, e.g. subtract and jump if 0. It was actually used in the SSEM, but it was not convenient or helpful to make programs small. Memory organization defines how instructions interact with the memory and also how different parts of memory interact with each other. During design emulation, software can run programs written in a proposed instruction set. Modern emulators running tests may measure time, energy consumption, and compile code size to determine if a particular instruction set architecture is meeting its goals. Computer organization. Computer organization helps optimize performance-based products. For example, software engineers need to know the processing ability of processors. They may need to optimize software in order to gain the most performance at the least expense. This can require quite detailed analysis of the computer organization. For example, in a multimedia decoder, the designers might need to arrange for most data to be processed in the fastest data part. Performance. Modern computer performance is often described in IPC instructions per cycle. This measures the efficiency of the architecture at any clock speed. Since a faster clock can make a faster computer, this is a useful, widely applicable measurement. Historic computers had IPC counts as low as 0.1 C instructions per second. Simple modern processors easily reach near 1. Superscalar processors may reach 3 to 5 by executing several instructions per clock cycle. Multi-core and vector processing CPUs can multiply this further by acting on a lot of data per instruction, which have several CPUs executing in parallel. Counting machine language instructions would be misleading because they can do varying amounts of work in different ISAs. The instruction in the standard measurement is not a count of the ISA's actual machine language instructions, but a historical unit of measurement usually based on the speed of the VAX computer architecture. Historically, many people measured a computer's speed by the clock rate, usually in megahertz or gigahertz. This refers to the cycles per second of the main clock of the CPU. However, this metric is somewhat misleading, as a machine with a higher clock rate may not necessarily have higher performance. As a result, manufacturers have moved away from clock speed as a measure of performance. Other factors influence speed, such as the mix of functional units, back speed, available memory, and the type and order of instructions in the programs being run. In a typical home computer, the simplest, most reliable way to speed performance is usually to add random access memory, RAM. More RAM increases the likelihood that needed data or a program is in RAM, so the system is less likely to need to move memory data from the disk. The disk is often 10,000 times slower than RAM because it has mechanical parts that must move to access its data. There are two main types of speed: latency and throughput. Latency is the time between the start of a process and its completion. Throughput is the amount of work done per unit time. Interrupt latency is the guaranteed maximum response time of the system to an electronic event, e.g., when the disk drive finishes moving some data. Performance is affected by a very wide range of design choices. For example, pipelining a processor usually makes latency worse, slower, but makes throughput better. Computers that control machinery usually need low interrupt latencies. These computers operate in a real-time environment and fail if an operation is not completed in a specified amount of time. For example, computer control anti-lock brakes must begin braking within a predictable, short time after the brake pedal is sensed. The performance of a computer can be measured using other metrics depending upon its application domain. A system may be CPU-bound, as in numerical calculation, 1-0-bound, as in a web-serving application, or memory-bound, as in video editing. Power consumption has become important in servers and portable devices like laptops. Benchmarking tries to take all these factors into account by measuring the time a computer takes to run through a series of text programs. Although benchmarking shows strengths, it may not help one to choose a computer. Often the measured machines split on different measures. For example, one system might handle scientific applications quickly, while another might play popular video games more smoothly. Furthermore, designers may add special features to their product in hardware or software that permit a specific benchmark to execute quickly but don't offer similar advantages to general tasks. study section summary. In this study section, we learned that when computer architecture involves instruction set architecture design, microarchitecture design, logic design, and implementation. 2. The discipline of computer architecture has 3 subcategories, which are A. Instruction set architecture, B. Macroarchitecture, computer organization, and C. System design. 3. The organization of computer components has effect on the performance of a computer system. This is the end of study section 3. Thanks for listening.